everyone, welcome back to this beautiful channel. My name is Namaila, and subsequently we actually received tons of information, tons of requests from several students urging us to actually start dealing with past question papers because of the jam factor. The time is already here and the time of the jam has been fixed. So the request goes like this, like please, we want you to guide us or teach us this jam past question paper so that we'll be able to handle our jam. Now we are drifting our intention from the classes which you are actually expecting back to solving questions in JAMB. Now what we have taken as a broad step is that we are not just going to solve those JAMB questions to you. We are not giving you the solutions to this question. What we intend doing is we are going to teach you the questions. After teaching you the questions, even before giving you the answers, you already know what these answers are. So that is the approach we intend to follow, and we hope you enjoy it. Please don't forget, subscribe, click on the notification bell so that you'll be the first to know when we are releasing these videos. Please stay with us. Alright, welcome back. Today we'll be solving physics past question. This is actually the nightmare of most science students. So today we're going to start solving these questions, and we chose to begin from 2010 because we know sometimes these syllables keep changing. So we're going to solve as much as we can, but we'll be growing from 2010 to 2011, 12, 13, 14 until we get to 2021. So now we're going to solve it, but before 2014, the JAM classes, the JAM exam is actually being written in the form of paper. They write it on paper, and then the types of these papers are changing. So the question number one has always been what paper type is given to you. So from 2010 until 2014, we're going to be skipping number one because number one is always making reference to the paper type which you're going to write, and that is like a bonus mark to everybody. So before 2014, every question is going to start from question 2. So now question number 2. So what I have here with me is the past question. We're going to start with question number 2, and the question number 2 says two cars moving in the same direction have speeds of 100 kilometers per hour and 130 kilometers per hour. What is the velocity of the faster car as measured by an observer in the slower car? And if you pay attention very well here, we have two cars in question here. We have car number 1 and car number 2. So car number 1 has a speed of 130 kilometers per hour, and car number 2 has a speed of 100 kilometers per hour. And in each of these cars, there are people seated in it. Now this question has to go back to relative motion, and they're talking about motion because you talk about the motion of one object relative to another object. Are you getting it? Now, a person sitting in a car, relative to him, the car is not moving. Are you getting it now? To him, it is the trees that are outside the car that are moving. So a person that is standing is observing these two cars coming with this speed. One is coming at 130 kilometers per hour, one is coming at 100 kilometers per hour. He's going to see that the one with 130 kilometers carries a very high speed, and they are going to pass him with a very high speed. Now you have these two cars. Now an observer is in the slower car, which is traveling with 100 kilometers per hour, and then the other car is moving at 130 kilometers per hour. Now you have two cars moving. Now one car relative to the other one is having 130 kilometers, the other one is covering 100 kilometers. So if you look at it, it means the other car is faster than the other one by 30 kilometers. Now by simply applying the mathematics here, we are going to find out that the first car 130 kilometers per hour, second car is 100 kilometers per hour. Now there is somebody seated in the first car. Now this person seated here in the second car, is observing this car to pass him by. Now they are asking you, at what speed is this observer going to see this car pass him by? Already he is covering 100 kilometers, and this one is covering 130 kilometers per hour. Now the difference between these two is simply 130 kilometers per hour minus 100 kilometers per hour. Are we getting it now? So now that is the speed difference between the observer in this car and the observer in the other car. Now the observers in this first car are going to see themselves moving 30 kilometers per hour faster than this one, and the observers in this car are going to see themselves moving. They are going to observe this car moving 30 kilometers more than theirs, because they're already taking 100 out of the 130 this particular car is covering. Let's assume we have somebody standing here. He's not in any car. He's going to observe the first car pass him at 130 kilometers per hour at a very high speed, and he's going to observe the second car passing him by at 100 kilometers per hour. Are you getting it now? So to him, the speed is equal to what they have, but to this observer in this car, he's seeing this other one to pass him at just 30 kilometers per hour. So whenever I see questions like this, it is actually questions on relative motion. All we need to do is to check the difference between the speeds. When we subtract them, we're going to get the answer to this. So 130 kilometers per hour minus 100 kilometers per hour gives us exactly 30 kilometers per hour. So this guy sees this car pass him at 30 kilometers per hour. Now question number 3 states, the diagram above shows a velocity time graph. The statement that is true about this motion is that the car A decelerates between points F and H, B accelerates between points F and G, C has a constant speed between points E and F, D has no acceleration between points F and G. So now we're going to carefully examine this motion, and then we'll discuss about it properly. Now this is the diagram here on the board. Now we're going to look at this diagram and explain how this speed, or how this velocity time graph, what it is actually representing. Now from point E to F, from point F to G, and from G to H, the total motion of this car is changing. So how does it change? Now let's assume I have a car and I just want to start moving. This car is parked at the front of my house, and I just put on the key and I start the car. Vroom, 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 vroom. Now I'm about to go. Now when I just start moving that car, you see, moment you see that when a person is starting a car, he normally keep on firing that car. Vroom. Now that high speed we are getting, that rise, is the point from E to F. Now the speed of this car is increasing. So whenever the speed is increasing or it is rising, then we say the speed is changing, and when speed changing, we call it acceleration. So this point is called the acceleration point. And now this car gets to a particular point where it is going to maintain the speed after firing. It will remain like that. So we say, this car is no longer changing its speed, and it is not decreasing. It is not increasing the speed, and it is not decreasing the speed. At that point, we say the car has uniform motion. Now uniform speed, sorry. Now at this point, we say the car has a uniform speed. That is the reason why at the top of this graph here, this loop here is very flat. It's telling you that it is not increasing and it is not decreasing. Are we getting it now? But when it started, it was high, it was going high, so that it gets to a particular speed, and when it gets to that speed, the car now is now all balanced. It will now maintain that speed and keep going. Now let's assume this car has gotten to its destination. What happens? It starts applying brake and it comes to a stop, and from point G to H, we see that this car is coming to a stop, point 0. Are we getting it now? So now this falling in speed is what we call deceleration. Now we have 3 points here. We have acceleration when the car is increasing in speed, we have uniform speed when it is neither increasing nor decreasing, and then we have deceleration where the car tends to come to a stop. Now we're going to look at the questions, and then we'll check the option which one is the right answer based on the little explanation I've given to you here. Now it says the diagram above shows the velocity time graph. So shows the velocity time graph. The statement that is true about this motion is that the car A decelerates between point F and H. If we look at point F and H, there was no deceleration. Deceleration is between point G and H. B says accelerates between point F and G. the point F and G was not acceleration, it was uniform speed. And then C says has a constant speed between point E and F. This is point E and F, there was acceleration, not a constant speed. And then D says has no acceleration between point F and G. So if we look at point F and G, there was no acceleration. All we had there was a uniform speed. I believe we understand this question. So any question twisted in this form, this is how it is. Then from this point to this point is always acceleration. From this point to this point is uniform speed, and from this point to this point is deceleration. This is a car starting. I hope we get it. So, okay, now let's look at question number 4. It says a stone and a feather are dropped from the same height above the earth's surface. Ignoring air resistance, which of the following is correct? Now I repeat the question again. A stone and a feather are dropped from the same height above the earth's surface. Ignoring air resistance, which of the following is correct? A says the stone and the feather will both reach the ground at the same time. B says the stone will reach the ground first. C says the feather will reach the ground first. And then D says the feather will be blown away by wind while the stone will drop steadily. Now if you look at these questions, it's a question of weight and in relation to air resistance. Now I'm going to carry out a very small practical to demonstrate what these questions actually stand for. Now I have 2 sheets of papers with me which I torn from the middle of the book. Now this paper and this paper are actually almost identical, both in shape and in size. Are we getting it now? Now what is the weight? We basically say that they approximately weigh the same. Now if I take this other paper and then I fold it into this and I show it to a student and I say between this and this, which one actually weighs more? And if I call this A and I call this B, most students will go for A being way more. Now if you look at it, it is basically the same paper or the same weight. Are you getting it now? Just because I'm strong does not mean I'm going to have more weight than before. Now there is a reason for that, why people think that this paper should have more weight, which is air resistance. Now if I basically take these 2 papers and I drop them to the ground, which one is going to go first? Is it A or B? Now for carry out this experiment, we're going to find out that A drops faster than B. Now why? It is because of the surface area. Now this one is so folded that little amount of air will have effect on it. Now when this other paper is falling down, it has to deal with the air resistance. And there is air coming and this paper has to sweep it off before it gets down. Why this one don't have to do that? Because it's totally folded, the surface area has been reduced, so it goes down faster. The reason why this one gained weight was because the effect of air resistance has been reduced on it by folding the paper, while this one don't go on time because it has to deal with so much of the air resistance coming to it. That is the reason why smaller cars are even faster than bigger ones, because their surface is so wide and they have to deal with so much air resistance coming towards them. While smaller cars have smaller statue and most of their the bonnet side is streamlined, and this area just comes, sweeps, and it goes away. And that's another chapter on its own, but we are considering this. Now if we go back to the question, now let us read the question and see what it says so that we understand. Now air resistance is actually a factor for determining the weight of every object. Now the air resistance has been taken off. Now what do we observe? Now the option says that A, the stone and the feather will both reach the ground at the same time. B, the stone will reach the ground first. C, the feather will reach the ground first. D, the feather will be blown away by the wind while stone will drop steadily. Now option D is totally out of the question because we're asked that there is no air resistance, but it's still capitalizing on air resistance. So in the absence of air resistance, both the feather and the stone are going to land to the ground at the same time. That is the simple answer. I hope my little experiment practically demonstrates to you how air resistance affects the weights of objects. Thank you so much. Now question number 5. Question number 5 states that a car moves with an initial velocity of 25 meters per second and reaches a final velocity of 45 meters per second in 10 seconds. What is the acceleration of the car? A says 5 meters per second, B says 25 meters per second, C says 20 meters per second, and D says 2 meters per second. Now the question is basically on acceleration, and we all know that acceleration can be defined as the change in velocity or the change in speed at a particular time. Now something happened to me. I was on my way back from a particular place. I was hurrying because it was about to be rainy, so I was hurrying home. I was moving at a particular speed. All of a sudden I came to a house and the gates opened and a very big a giant dog came out. So what happened, I had to increase my speed by running. So you see, initially I had the speed I was moving with, but when the dog came out I had to change the speed by increasing it. Are we getting it now? So simply when speed changes from initial to final, we said this change in speed is called acceleration. Are we getting it now? So the speed I was coming with initially is called the initial speed or the initial velocity, and the speed I now changed into after seeing the dog is now called the final speed or the final velocity, and this change happens at a particular time, so we must make reference to the time. That is the reason why acceleration is always defined as change in velocity. Imagine me before seeing a dog, I was moving. After seeing the dog, it increased. So that change in that velocity at the time it took for that change to happen, we call that change acceleration. So if somebody is walking and suddenly start running, we say he has accelerated. Are we getting it now? Now this is telling us that this change in velocity is telling us that there is a change to a final velocity and there was an initial velocity, and this change took place at a particular time. When you can solve this, that is very easy for you. So now from the questions, we were told that the initial speed this car was traveling with, is it a car? Now the initial speed it had was 25 meters per second, and then finally it had 45 meters per second, and all these things took place in 10 seconds. It means this car had initially it was traveling or was moving initially with 25 meters per second, and suddenly maybe it wants to overtake or something happened, it changes the speed to 45 meters per second, and this change took place in just 10 seconds. Now the change in speed is the acceleration, so they want you to calculate the acceleration that took place. So simply this is just the final, which is 45, so I've written here, minus the initial, which is 25, all over the time it took, 10 seconds. Are we getting it now? So 45 minus 25 is 20, and then this is divided by 10. 20 divided by 10 is 2, so it means the acceleration is actually 2 meters per second squared, meaning that option D is the right answer. I hope that answers the question. So let's move to the next question. Now question number 6. Question number 6 states that an object is weighed at different locations on the earth. What will be the right observation? Option A says both the mass and the weight vary. Option B says the weight is constant while the mass varies. Option C says the mass is constant while the weight varies, and option D says both the mass and the weight are constant. Now this is a dispute between mass and weight, and now what is the correct observation between mass and weight? What is their difference? Now mass simply means size, the size of an object. Are you getting it now? So my size is my mass, your size is your mass, the size of the board is its mass, the size of this marker is the mass. Now the weight of any object is the size acted upon by gravity. Are you getting it now? If an object is having a bigger weight, it has no relationship with the size. Now the issue here is that size, the weight changes, but the mass doesn't change. Now if a stone is falling under air, the weight it comes with is different from when the stone is falling underwater. Are you getting it now? You find out that if a stone is falling under air, you see it comes with a very high speed, but when it enters the water, the speed changes. It means the weight has changed in different medium. In air it has more weight, in water it has lesser weight. Are you getting it now? So now how do we come about this now? Mass, the size of an object, which is mass, does not change with the change in environment. Wherever you go, the size of something is always the same. If you take me to any part of the world, if you take me underwater outside the Earth to other planets, my size doesn't change. But you can see videos of scientists who go out, videos uploaded by NASA. You see scientists going outside the space, you see them floating, meaning they are totally weightless there, but their size remain the same. So wherever you go, mass is constant, but weight is changing. Are you getting it now? So now if we go back to the options, let's read the question again. It says an object is weighed at different location on the Earth. What will be the right observation? Are you getting it now? They say A, both the mass and the weight vary. We know mass doesn't change. It is weight that change. And B says the weight is constant while the mass varies. The weight cannot be constant because it is actually changing. And then C says the mass is constant while the weight varies. And this C is the right option because we know that the mass does not change, it is constant, and the weight varies. D says both the mass and the weights are constant. So option C is the right answer. I hope that answers the question. Okay, now question number 7. Question number 7 states, the diagram above represents balls in an undulating surface. Which of the following options represent positions of stable equilibrium? A says II, V and VII. B says II, V and VII. C says II, VI and IX. D says III, IV and VIII. Now, this is a question on equilibrium which I intend to explain briefly. Now, stable equilibrium. Now when we're talking about equilibrium, we basically have two types. We have dynamic, we have static, and that is talking about stability, where it doesn't jingle, it doesn't change, it is stable. Now I have drawn a seesaw here, a jingle over, which we normally call jangle over. Now this is a boy sitting here and this is another boy sitting here. Now if there is a weight difference, you see one going up, the other coming down, and so on and so forth. But if these two boys have equal weight, they are going to balance it in such that it will not go up, it will not come down. At that point, we'll say they are in equilibrium. Are we getting it now? Now this is a ball that is represented. The motion, the ball is represented on different points here, and then when you look at the position here, I, you find out that the ball will tend to roll down, and I is showing that the ball has rolled down. And if you look at point triple I, you're going to find out that the ball will be stable at this point. It cannot be stable at this point, and this point, because it will always roll down. And at this point, this point, this point, it is in the point of rolling. But at this point, this point, this point, it can't go up and it can't cross over. So if you look at it, we find out that the ball, based on the diagram, is more stable at points III, VI, and then IX. So if we go back to the option, we're going to find out that option C is actually the right answer. III, VI, and then IX. I hope that answers the question.